Assalamu alaikum. Dear learners, I hope you are doing great and are ready to dive into the world of robotics with me. This series of video lectures is aimed at introducing some very important tools which robotics or related field engineers are going to need extensively, especially during research work. Though the contents of this broad field may be widened quite a lot, however, we will limit our focus to MATLAB's Robotics System Toolbox and SimScape Toolbox. These two toolboxes are approximately everything you need to learn about various algorithms, test them in simulated environments, make your own simulated robots, and test their performance under various conditions. To understand things more concretely, I'll follow an example in which we are going to build a simple 2 degree of freedom planar robotic manipulator, and then we are going to simulate it using required robotics algorithms. Along the way, I'll explain each component I'll be using. So let me first explain what example I'm going to use and how I'm going to simulate the 2 degree of freedom planar robot arm. For the introductory video, we are going to keep things simple. Therefore, the robot arm that we are going to design and implement will look like this. It will have two joints placed over here and over here. The links joining the joints will have shown lengths, and as we wanted a planar robot, the end effector shown by this block will remain in the same plane, which is parallel to the ground and 0.1 meters above it. The shown figure over here is the front view of the robot which we are going to make. However, if we see from the top view, then the workspace of this manipulator would be a circle of radius 0.35 meters. Moreover, if we apply a rotation restriction on the second joint so that the second link and the end effector might not collide with the first link, then the workspace will become a disk as shown over here. Anyhow, to implement this robot in the simulated environment, we need some CAD tool that will build the required CAD model and insert the joints in the correct locations and orientations. This will be achieved by the SimScape Toolbox. After that, we need to drive this robot in its workspace. So, some kind of algorithm should tell the joints of the robot to rotate by a certain angle if we want to reach a specific point in the workspace. At the very basic level, there are two ways to achieve this. First, we can command the joints to rotate to a certain angle, which is within the rotation limit of the joint, and when the joints have rotated to those certain angles, the end effector would have reached a corresponding point in the workspace. This is what we call the forward kinematics algorithm. However, in reality, we know that where in the workspace the end effector should reach, but we don't know the angles through which each joint must rotate so that the end effector may reach the desired location. Moreover, sometimes there are multiple joint angles that will take the robot to the same point in the workspace. Therefore, it is a difficult task to provide joint angles directly, hoping that a robot will reach the intended location. To cater this, we need some other kind of algorithm that will take in the point in the workspace and generate the joint angles for the joints, which when traversed by the joints, the end effector will reach the desired location. This algorithm is what we call the inverse kinematics algorithm. In this introductory video, I'll showcase forward kinematics algorithm using Robotics System Toolbox only. Firstly, we will use SimScape Toolbox to create a CAD model of our robotic arm. This CAD model can then be used to generate a rigid body tree representation, which the Robotic System Toolbox requires for its working. Alternatively, you may generate rigid body tree representation directly, but that will be a difficult task at the moment because for that, you should be well versed with the coding techniques. Therefore, for starters, we will use a CAD model to generate the rigid body tree of our robot, which in my perspective is an easier approach. There are other advantages to this approach as well, however, I won't discuss those over here. So let's get started and I'll explain several basics along the way. So this is the Simulink environment on which we are going to work. Over here you can see that I have opened the Simulink library browser whereas over here I have opened a blank Simulink model. So first I am going to use SimScape Toolbox to design the CAD model of the robot, and then I am going to use Robotics System Toolbox to drive that robot through forward kinematics algorithm. If you scroll down a bit, you can see SimScape Toolbox right over here. Make sure you have installed it. Under the SimScape Toolbox, there are multiple subdivisions from which we are going to work in multi-body division. Inside the multi-body portion, we can find all the kind of elements that can be used to generate robotic systems or mechanical systems. Before creating anything in multi-body system, there are three blocks that are must for every kind of model. So let me place those three blocks and tell you that why they are needed. In the Utilities section under the SimScape, you can find Solver Configuration block. This will be used to define that what kind of ODE solver this mechanism is going to use. So we need this block over here. But right now in this example, we don't need to adjust any of the settings. Then we will move on to the frames and transforms under the multibody section, and over here we need to define a world reference frame. So we will need a world frame block. This frame will define the coordinate system of all the mechanisms which we are going to build. And at the end, in the utilities section under multibody, we will find mechanism configuration that will define the gravities or any other forces that are acting on all the mechanisms which are present in this model. So by default, if you double click the mechanism configuration, you will find that the gravity has been defined as minus 9.80665 in the z-axis. So we are not going to change this thing. So these three blocks are the basic blocks which are required for any kind of multi-body element or multi-body mechanisms which we are going to use or make using SimScape Multibody Toolbox. Now we are going to build the robot from base up to the end effector. So the first thing we need to build is the base. If you remember, the base was a simple cylindrical object. So I'm going to need a body element which can be found over here. And you can see that there is a cylindrical solid present over here. I can drag it over here, and by going into its settings, I can change its properties, its mass, its inertia, its size, and everything related to it. So for the time being, I'm going to enter 0.05 as its radius and its length as zero point 0.1. And in the graphics portion, as I've shown that its color was blue, so I'm going to use a blue color over here. So that's it. I have generated the base. Now the thing over here is that whenever you create any solid or any body in this multi-body environment, the frame of this body will be exactly at its center. So if I attach this cylindrical solid with the world frame, then the world frame and the frame of this cylindrical solid will be at the center of this body. But I want the world frame to be at the base of the body. So I need some kind of frame transformation between them. For that, I'll go to the frames and transforms, and I can use a rigid transform over here. This rigid transform will transform the world frame to the frame of the solid cylinder over here. So I can connect the world frame to the base portion, and the follower portion will be connected to the cylindrical object. But before that, let me rotate it so that I can easily connect it. The transformation over here should move the world frame at the center of the object. And as the height of the object was 0.1 meter, so I need to move 0.05 meter in z-axis. So inside the rigid transform, I'll go into the translation, and then in methods, I'm going to select Cartesian, and in the z-axis, I'm going to add 0.05. And that's it. Now at this point, my object should be lying. So therefore, I have attached a cylindrical solid over here. I'm going to attach the solver configuration block and the mechanism configuration block with this mechanism as well, like this. Let me rename this transformation block as world to base, because it is transforming the world coordinate system to base coordinate system. And this block is representing the base of the robot. Now the next thing is, on the base, I want to attach the first joint, but that joint should be at the top of the base. So I need to transform the frame of reference of this base from the center of it or from the middle of it to the top side. For that, once again, I'm going to use a rigid transform. So this rigid transform is going to transform from base to joint 1. So I'm labeling joint 1 as J1. And I know that joint 1 should be present right at the top of the base. So it should be moved upwards or in Z direction by 0.05. But to cater the height of the link as well, the first joint should be at the middle of first link as well. So first link, if I am going to use its height as 0.02 meter, then the middle of 0.02 meter would be 0.01. So that is the height I should add over here as well. So I'm going to use 0.06 instead of 0.05. So now the base frame will be translated to a point where I can join joint 1. So to add the first joint, I will go into the joints section under multibody, and over here I can find different type of joints. From these joints I need revolute joint because we are going to use 2 revolute joints only. So I can drag this revolute joint and place it over here. I'm going to label this joint as J1, and now after this joint I need to add link 1, or that is the first link. The first link, if you remember, was a long cuboid. So once again, I'm going to go into the body elements, and from here, I'm going to select brick solid this time. But before attaching this solid with the joint, I need to move the frame of the joint to the center of this brick solid, because the frame of the brick solid will be at its center. So I need once again a transformation block. For that, I'm going to use another rigid transform. I'll connect the base of this transform to the follower of the joint 1. Now I need to move in X direction, and it would be half of the length of the link that I'm going to use. So the total link length was 0.2 meters. I'm going to move by 0.1. Now I can attach the solid or the link over here. So before that, let me adjust its properties. First of all, let me rotate it, and now adjust other properties like size and colors, etc. So the size of this link will be zero point 0.2 in X direction, 0.02 in Y, and 0.02 in Z. That is the width and the height. And for graphics, I'm going to use a light green color. For example, I can use this color. So that's it. Now I've attached the first link as well. Now, in the way, if you want to see that what you are building, you can always run this file and see what you have built. So if you have gone wrong anywhere, you can adjust right over here. So let me run it and see what we have built till now. So this is something that we have built. This is the front view of the robot which we have built. We have a blue base and a first link which is attached over here. On this side, you can see that we have a world frame which is at the lower center of the blue base. Then there is a base which has a frame right at the middle of it. Then after that base, we have joint 1 which has frame over here which is just above the base. And then after joint 1, we have a solid which is link 1, and this link 1 has its frame right at its middle. You can change the camera view by right clicking over here and go to standard views, and you can choose any of these views. Let me use the isometric view. So this is the robotic arm which we have made. Right now it has only one joint and one link. So far so good. let us complete the robot by adding the join 2 and the link 2 as well. So after link 1, we need to add joint 2. Once again, join 2 will be added right at the end of link 1. So we need some kind of frame transform that will transform the frame right from the center of link 1 to the extreme edge of link 1. So once again, I'm going to use a rigid transform and I'm going to attach it over here. And I know that link 1 was of length 0.2 and I need to move in x-axis by 0.1 more so that I'll reach the end of the link 1. So I'm going to write 0.1 over here. Now this rigid transform will take me from the center of link 1 to the position where I can attach joint 2. Let me rename these transforms for clarity. So this transform is taking me from joint 1 to link 1, whereas this transform is taking me from link 1 to join 2. So now I can attach join 2 over here. Once again, I'm going to use a revolute join. So I can copy it and place it over here. So this is the join 2. And after join 2, I need to add link 2. And for link 2, I need to once again move the frame of join 2 to the center of the link 2. So once again, I'm going to use this kind of frame transformation. I'm going to copy it, use it over here and adjust its length. I know that the second link is of 0.15 length in total, so I'm going to use 0.075 in x direction so that I can move to the position where link 2 can be attached. So this transformation will take me from joint 2 to link 2. Over here now I can attach link 2 like this. Let me adjust the properties of this link. So I will add 0.15 over here and let me change the graphics so that link 2 will look a bit different from link 1. I can use any other color. Let me use this purple magenta color and that's it. So now I have added link 2 as well. So after link 2, I need to add a joint that will be a fixed joint, and with that joint, I'll need to attach the end effector. So I can once again go to the joints. I can use a fixed joint like a weld joint. I can find it over here. This weld joint should be attached right at the end of the link 2. So I need some kind of transform to transform me from the center of the link 2 to the end of the link 2. So I'm going to need this kind of transform. This transform is going to take me from link 2 to joint of end effector. And I will modify the length as 0.075. Now after the weld joint, I need to attach an end effector. For the sake of simplicity, the end effector will look like a simple block. So once again, I'm going to go into the body elements and use a brick solid. Let me rotate it. And I'm going to attach this brick solid with the weld joint. So I need to transform the frame of the weld joint to the center of this brick solid. The size of this brick solid would be 0.02 in all directions. So it would be like this, and I can choose its color to be black. So as the last thing, I need a transformation that will transform the end effector joint frame to the end effector object frame or the body frame. So this frame is going to transform the joint of end effector to the end effector. And this is my end effector. And I know that as the size of the end effector is 0.02 in all directions, I need to move by 0.01 in x to reach the center of the end effector. So that's it. I guess we have made the robot perfectly. Now just to confirm this thing, let me run it and see what we have made. So this is the robot that we have made. This is our base. It has its frame of reference at the center. This is our link 1. It has its frame of reference at its center. This is link 2, which has its frame at its center, and at the end this black box is the end effector. And you can click on J1. You can see that where joint 1 or the first motor or the joint is attached, whereas this is the joint 2. Now you must be wondering that why I have joined or attached the joints like this, in which they are having z-axis pointing upwards. Well, in SimScape or in most of the literature or most of the programs or the simulators, the revolute joints or any other kind of joints, they always rotate or move about z-axis. So if we are going to use a revolute joint, then that joint is going to rotate about its z-axis. So if z-axis is pointing upwards, then this joint is going to rotate and this body will be rotating about it. If I see the isometric view, it will look like this. So if you can see that z axis of joint 2 is pointing upwards, so this magenta link, which is link 2, is going to rotate like this in this direction and in this direction, whereas this joint 1 has a z axis pointing upwards, so this link 1 is going to rotate in this direction or in this direction. So that's it. We have made the CAD model of the robot. Now just to clean the things a bit, let me group these items because there are too many items over here. Let me group these things. So I can group this end effector like this, click on these, select these two blocks, right click on them and create a subsystem. And we can name this subsystem as end effector. And I can name this connection port as end effector port. This is the joint. These three blocks will comprise of the link 2, so I'm going to create a subsystem and name these things as link 2, and this connection would be joint 2 and this connection would be joint end effector. After this, these three blocks are going to comprise of link 1, so I'm going to name those as link 1. This connection would be joint 1 and this would be joint 2. These three blocks are going to be named as the base, and this connection would be the world frame, and this connection would be joint 1. So that's it. Now our robot is looking much more tidy. We have the world frame. This portion is defining the world frame and the overall configurations. Then we have the base. After base we have joint 1. After joint 1 we have attached link 1. Then we have joint 2. Then we have attached link 2. Then we have a joint for end effector, and at the end we have the end effector. That's it. Now we want to drive this robot using the Robotics System Toolbox. So let us first review that what Robotic System Toolbox is and what different algorithms does it offer. If you go a little above this SimScape Toolbox, you can find Robotic System Toolbox over here. If you expand it, you can see different things over here. We are going to work on manipulator algorithms because we have made a manipulator. So inside this manipulator algorithm, we have various algorithms that can be used with these manipulators. Along the course, I'm going to explain almost each one of them, but right now we are going to use one of them only, whereas in the utilities section, there are certain other things that can be used to generate trajectories on which the robot will move, and we have coordinate transformation conversion as well, which is a very important block because we will be needing to transform our frames or different kind of references from one frame to the other frame. So the first thing with the Robotic System Toolbox is that it needs a rigid body tree representation of any robot. So to generate a rigid body tree from this model, all we need to do is we need to create a small M file. That is, we need to run a certain function which I have written already over here, and this function is of import robot. In this function, you need to pass the Simulink model file that contains the SimScape model of the robot. So we have just named our file as dof2 underscore test1, and now I just need to run this file. Over here I have defined the TS, which will be later on used as sampling time, as 1 millisecond, and this import robot function will create a rigid body tree and will save it into a variable named as dof2 underscore arm. So let me run it, and you can see that dof2 underscore arm is a rigid body tree which has been created over here. Now this rigid body tree can be used in Robotics System Toolbox. So I'm going to once again create a blank model. So in this model, we need the robot and the algorithms and blocks that are required to move that robot. So first of all, I'll copy the robot from this file to this new model. And now what I need to do is I need to drive the joints which are present in this robot. As we have two joints that can be driven, that is joint 1 and joint 2, we need to make some adjustment to them so that they can accept input from some kind of algorithm or from some kind of blocks. If we double click this joint 1, we will have certain options over here. Among these options, I'm going to discuss very few of them. The first one is the limits. You can specify the lower and upper limit of rotations and some other properties of this joint. So the lower limit, right now by default, if you check this block, by default it is written that the lower limit of rotation is minus 90 degrees. So I will keep it like this, and if I check this box, that is specify upper limit, the upper limit bound in degrees is 90 plus 90. So that's it. So I have restricted my joint 1 to rotate between minus 90 and plus 90 degrees only. After that, how I am going to actuate this joint? So there are two options. Either I can provide the motion or I can provide the torques. So right now I'm going to provide the motion, which will be provided by input, and for the torque I will select automatically computed. At the end, in the sensing section, I can sense that what is the position of the joint at a current moment, what is the velocity, its acceleration, its torques, and all other things. So right now I am only concerned with the position, so I am going to sense the position. Now you can see that there are two additional ports over here in joint 1. One will accept the position commands in radians and the other one will output the position command in radians. Similarly, for joint 2, I can choose the same kind of options. For limits, let me change this limit to, for example, minus 60 and the upper limit to plus 60. And for actuation, I'm once again going to use for torque automatically computed and motion will be provided by the input. For sensing, I'm going to sense the position, and that's it. So now I need to provide the position commands to these two joints, and for that I will need to connect the Simulink models of Robotic System Toolbox or general Simulink blocks with this multibody blocks. As you might have noticed that these lines are a bit different than simple Simulink flow lines. In multibody systems or in SimScape Toolbox, the lines are or these systems are representing physical systems. That is why these lines are a bit different. Whereas the Simulink blocks, which are normal Simulink blocks, they represent Simulink systems. So these two systems are a bit different. So we need some kind of converters between Simulink systems and physical systems. So for that, we can use converters which can be found in SimScape utilities. Over here, you can find a physical system to Simulink converter and a Simulink to physical system converter. So I'm going to use a Simulink to physical system converter over here. double click on it, and I'm going to specify that what signal this thing is going to provide. So it is going to provide angle in radians. So I've selected radians, and as the joint will calculate torques itself, so it will need derivatives. So I need to provide second order filtering with input derivatives as well. So that's it. I need two of them because I need to use both of them with two joints. And once the joint has rotated, the sensor or the position sensor will sense its position and will output me the position. Then I need to move that position from the physical system to the Simulink so that I can use it in my further algorithms. So I need a physical system to physical Simulink converter. I'll attach one over here and one over here. So now let me lock everything inside a subsystem like this, and this input will be Q1, that is position for joint 1. This will be Q2, position for joint 2. This would be Q1 measured, and this would be Q2 measured. Now this is my robot. Let me label as robot. So now I need to provide two angles to this robot. Those two joints which are present inside this robot are going to move on those angles, and I'll measure those angles and see that whether my robot is moving on those angles or not, which I provided, and I'll calculate that what is the physical position in XYZ coordinates of my robot. So for that, first of all, I need to provide the angles. So to keep things very simple, I'm going to use a sine function generator. This sine block will provide one joint position, that is for joint 1, and a similar will provide position for joint 2. I'm going to label it as Q1. Now I know that my joint 1 cannot go beyond minus 90 and plus 90. So in radians, it would be something about 1.732 radians. So I need to have the amplitude of this sine wave less than that, because the joint 1 has limits and it cannot go beyond pi by 2 radians. So I can add amplitude of, let's suppose, 1.3. Its frequency should be added somewhat because I want the joint to rotate in one direction and then in the other direction and keep on rotating like this. I can label the frequency as, let's suppose, let's keep it 1. I need another sine generator for joint number 2. Let me change it a bit. Now I know that the second joint has limits of minus 60 and plus 60, that is pi by 3. It will be somewhere around 1 radian. So I need to have some value of amplitude less than 1 radian. So let me have it as zero point 0.6. Let me change its frequency as, let's suppose, zero point 0.7. And that's it. So this is the position command for joint 1, and this is the position command for joint 2. Now the robot is going to move, and the sensors are going to sense that at which position the robot has moved, and they are going to generate the angles. Now I'll take those angles and will provide it to the forward kinematics algorithm, so that the forward kinematics algorithm will calculate that at given angles where the end effector of my robot is. So for that, I'm going to go into the Robotics System Toolbox and then in Manipulator Algorithms, and from here I'll need Get Transform block. So this block requires two things. Number one, it will require the rigid body tree, because I have already said that the robotic system toolbox require rigid body tree. So we'll need to provide it with the rigid body tree, which we have already created, and the configuration. Configuration means that what joints or what frames are at what angles. So right now, because we have only two frames or two joints that can move, so we only need to provide these two angles to this configuration pin. So for that, I need to combine them. I'm going to use a mux over here to combine these two angles like this and provide it to the configuration box. If you double click it, you can specify the rigid body tree that this block should use, and we have a TOF2 underscore arm over here. And for the source body, because we want to measure everything with respect to the world frame, That is, we want to find that where the end effector is with respect to our world frame. So the source body would be the last body, which is the end effector, and the target body would be the first body, which is the base. So I have selected these two bodies and that's it. Now it will give me the homogeneous transformation matrix that will contain the orientation and position of the end effector. To extract the position information from the homogeneous transformation matrix, I'll need a coordinate transformation conversion block. Inside this block, I'll use the input as homogeneous transformation because I'm getting homogeneous transformation, and I need the output in form of translation vector. So it will give me the translation vector or the XYZ position of the end effector. So now at the end, I can use a scope to see all these things, that what is happening. And inside the scope, I am going to use three different graphs. I'll use the number of input ports as 3 and the layout as this one, and that's it. So what I'm going to show over here is that in the last graph, I'm going to show the XYZ position of the end effector. Whereas on the upper two graphs, I'm going to show the joint 1 position that I gave and the joint 1 position on which the robot moved. So I need the reference joint 1 angle, which is this one, and the measured joint 1 angle, which is this one. So once again, I need a mux over here to combine these two things. Like I can combine these two things like this and provide it over here. And similarly for joint 2, I need a mux. Once again, I can provide these two angles like this. So this one, I can label it as joint 1, and I can label this thing as joint 2, and this last one as XYZ position of end effector. You can hide these two blocks into one subsystem and name this subsystem as forward kinematics, because it is taking the angles of the robot and giving you the position of the end effector. That is what forward kinematics does. So that's it. We have created a robot. We have used the robotic system toolbox algorithms to measure the joint angles and then convert those joint angles into the end effector positions. Now let us run it and check what is happening. So you can see that our robot is moving because we were providing a sine wave to joint 1 and a sine wave to joint 2. So it is moving like that. And to see that what angles are being traversed, we can open the scope and see it over here. So this first graph is showing us the joint 1. The second graph is showing us the position of the joint 2, because there are two lines over here. There is one yellow line and one blue line, but they are completely overlapping. That is, whatever was the desired angle, the robot was moving on that angle. And then at the end, these three lines, yellow, blue, and red, they are representing the X, Y, and Z coordinate of the end effector. Because it is a planar robot, the Z coordinate should remain same, and if you remember the dimensions of our robot, the Z coordinate of the end effector's center point should be at 0.11, and you can see that this red line is right over here at 0.11 meters, whereas X, which is represented by this yellow line, and Y, which is represented by this blue line, these two things are changing. So the end effector positions are shown by these three lines, and you can see that in the whole simulation at any time instance you can find that where the end effector is. So to summarize everything at the end, what we did was we created a CAD model using SimScape Toolbox. Using that CAD model, we generated a rigid body tree that will be used by the Robotics System Toolbox for various algorithms. After that, we created the rigid body tree using a simple import robot function, which is from the Robotics System Toolbox, and then we provided some angles to the two joints of our robot using simple sine generators. The robot should ideally follow these two angles, and we measured that whether our robot was following those two angles or not, and we saw that thing on the scope as well. And for the forward kinematics, we took the positions or the angles through which the both joints have rotated and provided those two joints to the forward kinematics blocks from the robotic system toolbox, and that forward kinematic algorithm calculated the position of the end effector in x, y, and z plane. So dear learners, this was a very simple, straightforward introductory tutorial type lecture that has introduced that what these toolboxes are, what are its capabilities, and what are the basics of using these two toolboxes. In the later lectures or in the later course, we are going to implement multiple examples over here. We can implement many complex robotic algorithms and complex CAD models over here as well. So I'll recommend that you practice it a lot. You create your own robots, try to move those robots on your given trajectories and learn these things by playing with these things. Hopefully by the next video, you would have learned these things and we will be moving towards more complex systems so that we can understand the whole functionality of the robotic system in a greater detail. That's everything for this video. Thank you and take care.